Right now, somewhere online, a headline is screaming that NASA just confirmed something terrifying about the Voyager spacecraft, as if it happened this morning, as if Mission Control is still scrambling to understand what it just found. People are sharing it, arguing about it, reacting like it's breaking news from the edge of the universe. Here's the truth nobody wants to slow down and tell you. This discovery didn't happen overnight. It happened slowly, in pieces, over more than a decade, as two machines built in the 1970s kept drifting farther from home than anything humans have ever built, and kept sending back data that made scientists increasingly uneasy about what's actually waiting out there in the dark between the stars. Because Voyager didn't just find something strange. It found a wall of plasma hotter than the surface of most stars, sitting right at the edge of our solar system, in a place physics said shouldn't be that hot at all. And once you understand what that wall actually is, and what else Voyager has been quietly picking up out there since it crossed into interstellar space, you'll never think about the edge of our solar system the same way again. This is the real story behind Voyager's terrifying new discovery, the two nearly 50-year-old machines humanity somehow still hasn't lost contact with, and the unsettling picture they've been building of what actually surrounds us out past the last planet. Rewind to 1977. Two nearly identical spacecraft, Voyager 1 and Voyager 2, launch within weeks of each other on a mission that was only ever supposed to last 4 years. Fly past Jupiter and Saturn, take some pictures, send the data home, done. Nobody planned for what came after. Nobody expected these machines to still be transmitting from beyond the edge of the solar system nearly 5 decades later, using onboard computers with less processing power than a modern calculator, running on a power source that is slowly, irreversibly dying. Voyager 2 pulled off something that has never been repeated since. It used a rare planetary alignment to fly past Jupiter, Saturn, Uranus, and Neptune in a single continuous mission, becoming the only spacecraft in human history to visit all 4 of the outer giant planets. Voyager 1 took a different, faster path, using Saturn's gravity to slingshot itself up and out of the plane of the solar system entirely, sacrificing any future flybys in exchange for speed. That decision is exactly what let it become the most distant human-made object ever built, a title it still holds today. Both spacecraft carry a golden record, a physical disk, etched with sounds and images of Earth, greetings in dozens of languages, music from across human history, sealed with instructions for any intelligence advanced enough to find it and play it. Nobody who built that record expected it to still be relevant 50 years later. Nobody expected the spacecraft carrying it to still be working either. And yet, here we are. Along the way, before either spacecraft ever got near the edge of anything, they rewrote the record books on the planets themselves, and some of what they found still shapes how scientists think about the outer solar system today. At Jupiter, Voyager 1 spotted something nobody expected to see on any moon, an active volcano erupting in real-time ice on Io, making it the first confirmed volcanic activity ever observed anywhere in the solar system beyond Earth. Voyager 2 followed up months later and found that same volcano still erupting, proof that Io wasn't just scarred by some ancient, long-dead violence, but was a living, churning world, torn apart from the inside by gravitational forces from Jupiter itself. At Saturn, both spacecraft flew close enough to reveal that the rings weren't the handful of smooth, simple bands astronomers had been drawing for centuries. They were thousands of individual ringlets, braided, kinked, and shepherded by tiny moons whose gravity carved grooves into the ice and rock like a needle cutting a record. Then, in 1986, Voyager 2 became the only spacecraft in human history to fly past Uranus, and what it found there was almost as strange as the planet's own sideways tilt, a magnetic field wildly offset from the planet's spin axis, tilted by nearly 60 degrees and shifted far off center. Nothing like the neat, mostly aligned fields seen at every other planet Voyager had visited. 3 years later, in 1989, Voyager 2 became the only spacecraft ever to reach Neptune, and there it found a colossal Earth-sized storm system nicknamed the Great Dark Spot, along with the fastest winds ever recorded anywhere in the solar system, screaming across Neptune's atmosphere at speeds topping 2,000 kilometers per hour. On its way past, Voyager 2 also caught Neptune's largest moon, Triton, doing something nobody predicted from a moon that far from the sun, actively erupting geysers of nitrogen gas and dark dust several kilometers into its thin atmosphere, evidence of ongoing geological activity on a frozen world that should, by every reasonable expectation, have been completely dead. And then, on Valentine's Day 1990, with its planetary mission essentially finished and nothing left to gain scientifically, Voyager 1 did something that had nothing to do with data collection at all. At the request of astronomer Carl Sagan, mission controllers turned the spacecraft's camera around back toward the inner solar system it had just spent 13 years leaving behind, and took one final photograph before Voyager's cameras were switched off, for good to save power. In that image, Earth appears as a single, barely visible pixel, a fraction of a pixel really, suspended in a scattered beam of sunlight against the vast, empty dark. Sagan would later describe it as a mote of dust caught in a sunbeam. The entirety of human history, every war, every birth, every person who has ever lived, compressed onto a point of light smaller than anything the eye could resolve without knowing exactly where to look. No spacecraft before or since has ever turned around and photographed home from that kind of distance, and the image, now known as the pale blue dot, remains one of the most quietly devastating photographs ever taken by anything humans have built. By 2012, Voyager 1 had been traveling for 35 years, and it reached somewhere no spacecraft had ever reached before. The heliopause, the invisible boundary where the constant outward pressure of the sun's solar wind finally loses its fight against the pressure of the interstellar medium, the thin soup of gas and radiation that fills the space between stars. On August 25, 2012, Voyager 1 crossed that line and became the first human-made object to leave the sun's bubble entirely. Voyager 2 followed 6 years later, crossing its own version of that same boundary on November 5, 2018, at a slightly different location because the two spacecraft had drifted apart on very different paths. For scientists watching the data pour in, both crossings looked the same in one crucial way. Solar particles suddenly dropped off almost completely, and cosmic rays from deep space, the kind normally deflected by the sun's magnetic bubble, suddenly spiked. That was the confirmation. Both spacecraft weren't just near the edge anymore, they were outside it, floating in the space between stars, sending back the first direct measurements interstellar space has ever given anyone. Getting there wasn't a single clean line either. Long before either spacecraft reached the heliopause, they had to cross the termination shock. The point where the solar wind, still supersonic after streaming outward for billions of kilometers, abruptly slams into the surrounding interstellar medium and decelerates violently, the same way water piles up and slows the instant it hits an obstacle. Voyager 1 crossed that shock in December 2004 at roughly 94 times the distance between the Earth and the Sun. Voyager 2 crossed its own termination shock in 2007 at a noticeably closer distance, evidence on its own that the heliosphere isn't a perfect sphere but a lopsided asymmetrical bubble, dented and stretched depending on which direction you're measuring from. Beyond that shock lies the heliosheath, a turbulent churning transition zone where the slowed solar wind piles up against the pressure of the galaxy outside, and it was inside that heliosheath during the long, slow crawl toward the heliopause itself that both spacecraft first started registering the temperature spikes that would eventually become the so-called wall. And that's when things started getting strange, because interstellar space, the actual space between stars, wasn't supposed to be violent. It wasn't supposed to be hot. Most people picture it as cold, empty, silent, and infinite dark nothing. What Voyager found instead was a searing, high-energy region sitting right at that boundary, with plasma temperatures estimated between 30,000 and 50,000 Kelvin, hot enough to make the surface of most stars look mild by comparison. Some outlets have nicknamed it a wall of fire, and while that's not literally accurate, since there's no actual flame and nothing burning, the number itself is real, and it's exactly the kind of detail that makes scientists sit up and start questioning their models. Here's the part that should genuinely unsettle you. Neither spacecraft was destroyed by it. Neither one was even damaged. That's not because the number is wrong. It's because the region is so thin, so close to a vacuum, that even though individual particles are moving at blistering extreme temperature speeds, there simply aren't enough of them, colliding with anything to transfer that heat the way it would on Earth. It's less like flying into a bonfire and more like being struck one atom at a time by particles moving faster than almost anything else in the solar system, spread out across so much empty space that the spacecraft never actually feels the burn. Voyager flew straight through a region hot, enough to vaporize steel, and came out the other side completely intact simply because there was almost nothing there to touch it. But the heat wasn't the only thing waiting at that boundary. It was the magnetic field that really broke the model scientists had been using for decades. Before Voyager crossed the heliopause, the assumption was straightforward. The sun's magnetic field, carried outward by the solar wind, would point in one direction inside the heliosphere, and the interstellar magnetic field, generated by forces completely outside our solar system, would point in a noticeably different direction outside it. That difference was supposed to be one of the clearest signs you'd crossed the line. Instead, Voyager 1 measured something nobody predicted. The magnetic field just outside the heliopause was aligned almost exactly with the magnetic field inside it. Voyager 2 crossed a completely different point on the boundary 6 years later and confirmed the same unsettling pattern. Two independent measurements, taken years apart, at different locations, agreeing on something that wasn't supposed to be true. Nobody has fully explained why. One possibility is that the heliosphere's own magnetic field is somehow dragging and reshaping the interstellar field around it as it plows through the galaxy, smoothing out a difference that should be obvious into something that barely registers. Another possibility is that our models of how magnetic fields behave at that boundary are simply incomplete, built on assumptions that only held up because nothing had ever actually measured the truth before. Either way, the boundary between our solar system and the rest of the galaxy turned out to be far leakier and far messier than anyone designing those models had guessed. Voyager 2's instruments went even further, detecting particles slipping through the heliopause in both directions, cosmic rays getting in more easily than expected, solar particles occasionally leaking out, turning what scientists once pictured as a clean, sealed boundary into something closer to a permeable membrane. Letting things through it was supposed to block. And then there's the sound. In 2012, right as Voyager 1 crossed into interstellar space, one of its remaining functional instruments, the plasma wave subsystem, started picking up something nobody expected to still be capable of detecting anything at all. A faint, continuous hum. Not a sound in the way your ears would recognize it, since there's no air in space to carry sound the way it travels on Earth, but a vibration in the charged particles surrounding the spacecraft translated into an audio signal scientists could actually listen to. It's the sound of interstellar plasma itself gently oscillating, a persistent, low background hum that never fully stops. Scientists compared it to a steady, gentle rain, a constant murmur underlying the emptiness, occasionally interrupted by sudden bursts triggered by solar outbursts reaching that far out, sounding, in their words, like a lightning strike in a distant thunderstorm before settling back into that same quiet hum. That discovery mattered for a reason that goes beyond how eerie it sounds. Before Voyager picked up that hum, scientists could only measure the density of interstellar plasma when something dramatic happened, like a solar shockwave rattling the region enough to register. That gave them scattered, occasional snapshots. The hums changed everything because it's constant. It let scientists track the density of the material surrounding Voyager continuously for the first time ever, turning years of silence into a steady stream of usable data about a region of space nobody had ever been able to listen to before. And what that continuous listening revealed is where this story gets genuinely disturbing. Starting around 2013, just after Voyager 1 crossed the heliopause, the electron density in the plasma surrounding it began climbing, not slightly, not within any margin of error anyone expected. By around 2015, the density had increased by roughly 40 times what it had been when Voyager first arrived in that region. And it has stayed elevated in that higher range ever since, with fluctuations, but no return to what scientists originally assumed interstellar space near our solar system should look like. A 40-fold jump in the density of the material surrounding a spacecraft that's supposed to be floating through nearly empty space is not a small anomaly. It's the kind of number that forces you to rewrite the assumptions you built your model on. Nobody is entirely sure why. One leading idea is that the heliosphere itself is compressing the interstellar medium around its outer edge, the same way a ship pushing through water piles it up and thickens it just ahead of the hull, meaning the density increase isn't a property of interstellar space generally, but a local effect caused by our own sun's bubble, shoving up against the galaxy around it. Scientists are still working to build a physical model that fully explains the mechanism producing that hum and that density spike together, which means, more than a decade after Voyager first started measuring it, this is still an open, unresolved question, sitting there in the data, waiting for someone to explain it properly. There's a bigger, quieter unease sitting underneath all of this too, one that has nothing to do with temperature or density and everything to do with distance and time. Voyager 1 is now more than 25 billion kilometers from Earth. Its signal, traveling at the speed of light, takes over 23 hours just to reach mission control, meaning by the time engineers on Earth read any new data, Voyager sends, they're not looking at what's happening to the spacecraft right now. They're looking at something that already happened nearly a full day earlier. Every single measurement humanity has of what's waiting out past our solar system is, by definition, already old news by the time anyone gets to see it. And Voyager almost stopped talking to us entirely. In November 2023, Voyager 1 suddenly started transmitting nothing but meaningless, garbled static back to Earth, a signal that made no sense, generated by a corrupted chip inside one of its onboard computers, a fault in hardware built in the 1970s that engineers could not simply walk over and replace. For nearly 5 months, humanity's most distant machine was effectively talking gibberish for more than 15 billion miles away, while a team of engineers, several of whom hadn't even been born when Voyager launched, worked out how to remotely relocate the spacecraft's code around the broken chip, sending fixes across a gap so wide that every single command took almost a full day just to arrive, with no way to know if it worked until another day passed waiting for the reply. In April 2024, the fix worked. Voyager 1 started making sense again. It was, by any reasonable definition, a near-death experience for a machine drifting through the coldest, most isolated environment humans have ever sent anything into, and it survived only because a small group of engineers refused to let a 50-year-old spacecraft die from something as mundane as a bad chip. That same year, engineers made another discovery that should unsettle anyone who assumes these missions are simply coasting toward a quiet, predictable end. In 2025, mission controllers managed to reactivate one of Voyager 1's backup thrusters after more than 2 decades of complete inactivity, a thruster nobody had used since 2004, brought back online specifically to help keep the spacecraft's antenna pointed at Earth as its primary systems continue to degrade. It worked. A piece of hardware built before most people alive today were born, silent for over 20 years, powered back up across billions of kilometers, and did exactly what it was designed to do. That's not something you'd expect from a spacecraft that was only ever built to survive 4 years, but that success comes with a countdown attached. Both Voyager spacecraft run on radioisotope thermoelectric generators, power sources that convert the heat from slowly decaying plutonium into electricity, and that decay never stops, never pauses, never waits for anyone. Every single year, both spacecraft lose a small amount of available power, forcing engineers to make brutal one-way decisions: which instrument to permanently switch off next, which heater to disable and risk freezing a component that can never be repaired, which capability to sacrifice in exchange for a few more months, maybe a few more years, of any signal at all. One by one, instruments that once helped map Jupiter's storms and Saturn's rings have already gone dark, not because they broke, but because there simply wasn't enough power left to keep them running alongside everything else. Engineers now widely expect that by sometime around the end of this decade, both Voyagers will finally run out of enough power to transmit anything back to Earth at all, going permanently, irreversibly silent, still moving, still carrying their golden records, but no longer able to tell anyone what they're seeing. And once that silence happens, it will not be undone. There's no rescue mission. There is no way to fly out and repair a spacecraft that far away, moving that fast, with technology that predates almost every engineer currently working the mission. Whatever Voyager 1 and Voyager 2 have already sent back is quite possibly the last direct, in-person data humanity will have from that exact region of interstellar space for decades, maybe longer, since nothing currently funded is built to travel out that far and keep transmitting once it arrives. That gap is exactly why other missions have quietly picked up pieces of the work Voyager can no longer do alone. The Interstellar Boundary Explorer has spent years watching the heliosphere from a safe distance, mapping its outer shape indirectly by studying particles bouncing back from the boundary rather than flying through it directly. More recently, a newer spacecraft called the Interstellar Mapping and Acceleration Probe was launched to study that same boundary in far greater detail, effectively picking up the question Voyager first raised but never had the instruments to fully answer. None of them, though, actually crossed the line the way Voyager did. None of them sit inside interstellar space itself, feeling the plasma, hearing the hum, measuring the density directly the way only a spacecraft that has physically left the solar system ever can. For now, and for the foreseeable future, Voyager 1 and Voyager 2 remain the only direct witnesses humanity has ever had to what's actually out there. There's something almost unbearable about the arithmetic of it all, once you actually sit with the numbers. Every command sent to Voyager 1 takes over 23 hours to arrive, and every reply takes another 23 hours to come back, meaning a single question and answer, something that would take a fraction of a second between two people in the same room, takes nearly 2 full days to complete across that gap. The engineers currently keeping these spacecraft alive are, in a very real sense, having the slowest conversation in human history, one exchange at a time, with a machine that predates most of their own careers, about a place in space that no human being will likely visit directly for generations, if ever. So here's the real shock. Once you strip away the fake urgency and let the actual story sink in. 2 machines built in the 1970s, designed to last 4 years, are still out there, still transmitting, still measuring a boundary between our solar system and the rest of the galaxy that turned out to be hotter, denser, leakier, and stranger than anyone predicted before they got there. A wall of plasma tens of thousands of degrees hot that can't burn anything because there's almost nothing there to burn. A magnetic field that shouldn't align but does. A hum in the dark that let scientists hear density spikes nobody expected. A spacecraft that went silent nearly for good and was talked back to life by engineers relaying commands across a gap so wide that every question takes a full day just to be heard. And a power source ticking down second by second toward a moment sometime in the next few years when both of these machines will finally stop talking to us for good, carrying humanity's message to the stars into a silence nobody back home will ever get to hear the other side of. Somewhere out past the edge of our solar system right now, Voyager 1 is still moving, still measuring, still sending back a signal that takes nearly a full day to reach anyone. Whatever else is waiting out there in that thin, searing, unexpectedly loud stretch of space between the stars, humanity built two machines that found it first, and for a little, while longer, they're still the only ones listening.